to definition check generics, presented by Chandler and Josh, who are on stage before the break, and myself. We are part of the Carbon team. And in part one, Josh and Chandler introduced you to check generics, and hopefully got you very excited about them. Like maybe you think this is a feature you want in a language now, so that's great. In this part, Josh and I are going to dig into some of the interesting and non-trivial details that come about when you try to implement definition check generics in a language. The subtitle of part two is the how of check generics, but unofficially the subtitle is check generics are hard. So we're going to focus on 4 hard problems in check generics. These are the type equality problem, termination, coherence, and specialization. And we're going to explain what each of these means when we get to it, why it's hard, how it's handled by the generic systems in Swift and Rust, and how we approached it in Carbon. Now, Carbon's generics system and its generics design has benefited a lot from the open design discussions of other languages. We're super grateful for the languages that have made their design processes open and available for us to look into through things like talking about things on GitHub, on blog posts, and just having like really great detailed design documents explaining what they did and why they did it. And we hope that this talk is going to contain some ideas for future languages to use as well, so that we can pay forward the debt that we owe to the languages that came before us. And we think that Carbon has some novel solutions to the problems that we're talking about, and these solutions improve on the status quo of the prior approaches. So the first problem we're going to talk about is type equality. And type equality in a check generic system is hard, and it sounds like it's probably a very easy problem, because like, how hard can it be to tell if 2 types are the same? You just look at them, either they're the same or they're not, right? But actually, it's not that easy. So in part 1, we saw that we have interfaces. And interfaces describe constraints on a type. And in other languages than Carbon, these might be called concepts or traits or protocols, but the idea is the same. We're describing a set of constraints on a type. And interfaces can include types themselves. So we say an iterator has an associated type called value type, and container has a value type and an iterator type. And sometimes we want to constrain that these associated types have particular values. So in this case, we're saying, in order for a type to be a container, it's going to have a value type, it's going to have an iterator type, but the value type of the iterator must be the same as the value type of the container. Does that make sense? Okay. So more generally, the situation that we have is we have some type expressions that we know must be equal. So how do we determine if 2 types are equal? And given this setup, can we actually always determine this? Ideally, this should always be possible. We don't want the answer to the question of, are these 2 types the same, to be that we don't know, because that would mean the answer to the question of, is this a valid program, might be that we don't know. And that's not ideal. But this is going to be a hard problem. So the setup is we're given arbitrary constraints where we're saying this type expression a.b equals c.d. And we want to know, does that mean that the type t is the same as the type u? And we can view these constraints as sort of rewrite rules that apply to type expressions. So we can rephrase this problem as, given the set of rewrite rules, can we rewrite one string to another string? And maybe for some people with backgrounds in theoretical computer science or pure maths, some alarm bells are going off right now. Let's get to that. Okay, so this is a simple example. We have an interface X, and X has 2 associated types. It's got A and it's got B. And A and B both also satisfy the interface X. Now suppose we also have the rule that x.a.b equals x.b.a. It's a fairly simple thing that you might set up. And so this is going to mean that some slightly more complex equations also hold. So x.a.b.a is the same as x.a.a.b because we can rewrite the final a.b into a b.a in either direction. And more complex expressions also hold. So in this case, after performing a series of rewrites, we can turn the thing on the left into the thing on the right. And you can check that, or you can just trust me. But more generally, what we have here is that we can reorder arbitrarily A's and B's. And types are going to be equal then if they have the same number of A's and the same number of B's. And this setup with types exactly models a particular semigroup which has two generators, A and B, and this relation AB equals BA. And then type equality is the word problem for that semigroup. And any finitely generated semigroup can be modeled in this way by turning it into associated types with relations between them. Okay, so let's look at a more interesting semigroup. There's a semigroup in a paper from 1957. This is kind of an interesting one. It translates into an interface with 5 associated types and 7 relations between them. And the interesting thing about this particular semigroup is the word problem for this semigroup is unsolvable. That means that there are words, which are sequences of letters from the semigroup or sequences of associated types, for which you cannot tell whether one word is the same as another word. It's mathematically impossible to determine. And that means that type equality in this system with this set of constraints is undecidable. We cannot determine whether two types are the same in general. And worse than that, even telling whether you're in a case like this, whether you're in one of these hard cases that has an undecidable word problem, is itself undecidable. And yet, Swift and Rust both allow you to model this in their type system. So what do? Let's look at Swift first. Swift permits an arbitrary equality constraint to be specified on associated types with where clauses. And this setup, which is reduced from the Swift standard library, produces an infinite family of types that are all equal. And that leads to a problem, which is type checking Swift becomes undecidable. And in fact, the example on the previous slide is taken from this post to the Swift forums in 2020. And the reduction into semigroups was also introduced here. So this blog post also suggested that we do something different in Swift, and what they decided to pursue was the Knuth-Bendix completion algorithm. And so what this does is, given a protocol, or I think in general a collection of protocols where the associated types refer to each other, it computes an efficient procedure for rewriting types into a canonical form. And this algorithm is either going to take your protocol and accept it and form rewrite rules that can then correctly handle all cases, or reject and say, this is impossible, or it might run forever. And Swift responds to the running forever case by applying an iteration limit. And so this is a huge improvement, right? This means that if you're going to get an error, you're going to get an error when you define the protocol. You're not going to get an error when you use it. But it's still undecidable whether a protocol is valid or not. And lots of common examples work. Swift, I don't think, has had huge problems with this rejecting things that they want to accept. But it is hard to characterize what's going to work, what's not going to work. And it's also hard to give an error which says what's wrong and actually how to fix it when things go wrong. OK, and next, Rust. So Rust lets you constrain the value of an associated type. And you do that when you use a trait by putting an equation in the angle brackets after the trait name. Rust only lets you constrain the associated types of that trait, not more complex expressions. There's syntax for more complex expressions, but it's not implemented in Rust C yet. But it turns out that this is still sufficient to allow you to express all the hard cases. And it's not entirely clear what algorithm Rust is using to deal with this. But like with Swift, there does seem to be a recursion limit. In cases like this, where we have a.b equals b.a, Rust would be OK with this. But if you also add the constraint that b.a equals a.b, which seems redundant, it seems like it shouldn't be harmful, Rust gets an overflow while looking at this trait. And as I say, it's not entirely clear what rule Rust is using. I checked the Ferrician spec and it doesn't say. And there's a second implementation of the Rust traits system called Chalk, which does accept this case. So it seems like maybe it's actually underspecified. And so there's no guidance in Rust on how you write self-referential constraints that are actually going to work. What the Rust guide says about this error E0275 is consider changing your trait bounds so they're less self-referential. Not super useful. Okay, so what do we do in carbon? So for carbon, we wanted an approach that is decidable and that's efficiently decidable. And we want something that's comprehensible so our users can understand what's going on, why we're accepting things, why we're rejecting things. And we also want it to be a rule that's general. We don't want to say that you can't treat these two types as equal if you can prove that they are equal. And this is a hard problem. So we decided we'd split the problem into two parts. One part is we're going to have a sort of addressing the 90% case, an ergonomic solution that for the cases where you don't hit the hard problems will just automatically do the right thing. And then for the remaining cases where you are in one of these tricky situations where there might be some kind of cycle of types getting more and more complex, we're going to have a general solution so you can still handle that. But it may be less ergonomic. So for the easy cases, we're going to use an approach that's somewhat like Rust, where when you introduce a use of an interface, you can specify a rewrite rule on it. So in this case, we're saying when we introduce iterator type, its dot element is the element of the sequence. So that means that whenever we see a sequence.iterator type.element, we're going to rewrite that to sequence.element. This allows us to constrain only the immediate associated types of an interface. And we also do not allow you to constrain the associated types of an incomplete interface, so one that we haven't finished processing the definition of yet. And that means that there can't be any cycles between associated types in the same interface or across interfaces. There can still be cycles between constraints on associated types in the same member. So you could have, in subsequence, you could have two dot something equals rules that refer to each other. And those are easy to detect cycles. So we can find all cycles, we can eliminate them all. And a consequence of that is that whenever you have this set of rewrites, the rewrite sequence must always terminate. So for example, we can have a setup like this, where we have rewrites in an interface, we have a rewrite in a function, we have a rewrite in an impl, and we can ask, what is the return type of this function f? So we start off with C subsequence iterator type element. And C.subsequence doesn't have a rewrite rule, but C.subsequence.iterator type does in this interface. And so we know that that iterator type is supposed to be rewritten to the iterator type of the sliceable sequence, which takes us to C.iterator type. And then we have a rewrite for C.iterator type that takes us to I32 star. And so we perform that rewrite. And then we find the impl for I32 star as iterator, and that has a rewrite for the element to T, which in this case is I32. And so we rewrite the return type of f to just I32, which is the result that we were looking for. So not all constraints can be written in this way. There are some restrictions on what you can write, and that's necessary for this to be a decidable rule. But what we've found is that most constraints that we've seen in practice can be, including a wide variety of constraints that occur in things like standard libraries. And this produces a canonical type by performing this sequence of rewrites. And that's super useful for us for another reason, which is that we use that canonical type to determine what members you find when you apply a dot to an expression. But this isn't complete. We still want an answer for the hard cases where this doesn't apply. And for that, what we do is we have a single-step equality constraints. And these are written with a double equals. And you think of these not as an assignment or a rewrite, but more as a comparison. We're saying, in order to specify this, you've got to prove that these types are equal, but we're not going to treat them as being the same type. We're going to treat them as two types that we happen to know have this relationship between them. And so what that means is the compiler will allow an implicit conversion between these two symbolic types, no-op implicit conversion that won't generate any code or result in any runtime changes. It's just a change of the way that the compiler is thinking about the type. So for example, we can convert C.iterator type.value type to C.value type because we have an equality relationship there. And we can convert C.value type to W. We can do this in two steps, one for each equals constraint. And more generally, if types that are known to be equal occur as components in other types, like if we're trying to convert between a vector of t and vector of u, and we know t equals u, then we allow that as a single-step conversion as well. But we do not compute a transitive closure of these rules. This is similar to the way that the C++ rule works, where you can have at most one user-defined conversion in a sequence. So we can't go directly from C iterator type value type to W. If you want to do that, we have a feature to make that a little bit easier. So we have this observed declaration. And the way that this works is that you can specify a chain of equalities, and the compiler is going to check that it can see that each of the equalities in this chain holds. So it knows C's iterator type's value type is C's value type, and it knows C's value type is W. And then once it's satisfied with that, it'll add to its kind of typing context the fact that everything in this chain is equal to everything in this chain, which means that after this line, we are allowed to implicitly convert from C.iterator type to value type directly to W in a single step. Okay, so this single step equality rule is fully general. In any case where there are two types that are equal and that you can prove are equal through a series of individual steps, you can convince the compiler of that fact, although the compiler isn't going to go looking for that proof for you. It's efficient to type check because we're looking only in a fairly small set of equality relationships to determine if two types are equal. But on the other hand, it's not super ergonomic in the cases where you actually do need to convert through more than one step in the chain. And you may sometimes need to add or want to add observed declarations to make that easier. The good news there is the compiler can do kind of a best effort search for a proof, and it can say, hey, here's an observed declaration you should add to the code just to capture this. And of course, it's not transitive, which might be a little bit surprising. But the rule, I think, is at least easy for people to understand. And so we can say, this is what went wrong. This is what you need to do to fix it. OK, so summary is, type equality in check generics actually turns out to be hard, and maybe harder than we expected going into this. The Swift rule is undecidable, and hard cases can hit an iteration limit. The Rust rule is also undecidable, and hard cases can hit an iteration limit. Carbon has a decidable rule, but the downside is the hard cases are less ergonomic, and actually more cases are in this hard cases side of things than they are for the other two languages. John?
Do you find that users understand when to use one rule rather than the other?
Do we find that users understand when to use one rule rather than the other? Our advice is to use a rewrite rule whenever you can. That's a fairly easy advice to give people. But the downside is that that means the double equals cases are rare enough that perhaps people are surprised when they come up.
What are the risks of getting the double equals incorrect?
What are the risks of getting the double equals incorrect? What do you mean by incorrect here?
Like, for example, perhaps writing that one type A can be equivalent, is equal to another type B, but that type B was not what you intended. It might be an unrelated type or type rows.
So the question is, what are the risks of writing a double equals constraint that turns out to not actually be true? So whenever you write a double equals constraint or a single equals constraint, there's actually two different things going on there. One of them is you're saying, when you're in the scope of this constraint, you get to perform this rewrite, or you get to assume these two types are the same. The other one is whenever you are calling some utility that has that constraint on it, whenever you are asked to provide something that satisfies that constraint, the compiler has to be able to prove at the point of that call that the constraint holds. So there is no case where you can call a function that has a constraint where the constraint is not satisfied. But it does mean that there is this extra burden on the caller. Does that make sense?
Thank you.
Great. OK, so that's type equality. And in Carbon, we believe we have a rule that is total, where we can always determine whether two types are equal, that will always terminate. But maybe that's not so useful if type checking as a whole doesn't always terminate. So for that to be really useful, what we'd like is for the rest of type checking to also always terminate. So the problem we're looking at is something like this. And what this impl is saying is a type T implements an interface that I'm calling interface if the type T star implements that interface. And that's a problem because the type T star will implement that interface if the type T star star implements that interface, and so on forever. And we can express arbitrary computation in this way. So we can say a Turing machine halts in one state with one tape, if it halts in another state with another tape, and so on. And so, this is a completely general Turing-complete way of performing computation in the type system. And as before, ideally, we want the answer to the question of, is this a valid program, to not be that we don't know, that we can't work it out, that it's not computable. So we probably don't want to allow this kind of, especially accidental, Turing completeness in the type system. So what can we do? Well, one alternative would be to say, we're not going to worry about it. We're just going to do nothing, ignore the problem, and if you hit one of these cases, the compiler will run out of memory or time out. And this appears to be what the Swift compiler currently does in at least some cases. So I've set up examples where the Swift compiler will basically crash saying, ran out of memory, sorry. And it'll point you to a place in the source, but the diagnostics aren't amazing, don't really explain what the problem was. Another option, which is popular in C++, is to use a recursion limit. So for example, in C++, you can write a template that has this problem where the template recursively calls itself, and it just instantiates more and more complex templates, and you get errors like this. And the same thing seems to be used for Rust, where the same thing comes up. It says, consider increasing the recursion limit. OK. So recursion limits. They're perhaps not an ideal way to solve the problem. One of the issues is they tend to be brittle, in that a small change to the source can cause you to start hitting the limit when you didn't before. And in particular, when there are recursion limits that people sort of know, there's a tendency for people to write code that gets up to but not quite over the limit. And then a small change to the code or a small change to the way that things are set up can suddenly cause you or your users to go over the limit. In C++ at least, there's also order dependency due to caching. So if you have a template instantiation earlier on in a file that maybe does some recursion, and then an instantiation later that uses the result of that first one, then that might work. But if you reorder those two declarations, then the recursive depth of the second computation, which is now first, may be so great that it goes over the limit. And so that's not ideal. Another issue is that the recursion limits tend to not be composable. So if you have two libraries that are both staying under the limit independently, but then one of them goes some distance deep in its recursion, and then triggers the recursion in the other library, then you can go over the limit when you combine the two. Mm-hmm. And finally, the diagnostics you tend to get out of these systems are pretty verbose. They show you, hey, I got into this hugely complicated situation before I found out that something was wrong and I hit my limit. And you often get a wall of fairly uninformative text. Right? So what do we do about this? Well, another option we could take would be to just disallow recursion entirely. And that would certainly solve the problem. We could say, if when you're checking an impl, you recursively get back to checking that same impl again, yeah, maybe things have gone wrong. Maybe we should just stop there. And then that would terminate because there's only finitely many impl declarations in the program, and so you can't go on forever that way. But it also rejects use cases that we care about quite a lot. So for example, we might say, if you have a type T that's hashable, then vector of T should be hashable, right? Makes sense. Mm-hmm. But then what happens when you try to hash a vector of T? First we're going to say, well, vector of T is hashable if vector of T is hashable, vector of T is hashable if T is but wait, we're already checking that impl, so we would reject. That's not good. So what we're looking at in Carbon is a refinement of that approach where we want to disallow recursion where we think we're not making progress. So we're going to allow recursion, but only if we don't reach a step where we get back to the same impl, and the query that we're trying to satisfy is, in some sense, strictly more complex. And we're also going to terminate if we see a cycle, because it's obviously not going to make progress if we see a cycle. So what do we mean by strictly more complex? Well, suppose we've got a query like this, where we're saying, is vector of I32 star hashable? What we want to do here is look at the labels in this, where a label is something like vector or I32, or the star that's constructing a pointer type, or the hashable interface. And we want to count the number of times each of those appears. And so we've got two vectors, one I32, one star, one hashable. And then when we see that we're arriving back at the same impl with a different query, we're going to do the same count. And in this case, we've got one vector, one I32, one star, one hashable. And we will reject if none of these counts have got lower and at least one of them has got higher, which is to say that considering the labels in this query as a multiset, if we got to a strict superset of that multiset, then we're not making progress. So in this case, we would allow this because we haven't hit this bad case. But if we were to go in the other direction from vector of I32 star as hashable to vector of I32 star as hashable, then we'd reject. We'd say, this isn't going anywhere. We're going to stop right now. And this will reject some things that could potentially terminate. Like maybe there's an impl for vector of I32 star as hashable somewhere in the program. And so maybe we would be able to eventually stop, but we think this is a good criterion for not making progress. Okay, so we've been able to prove that this constraint guarantees termination. And basically the way this works is there's only a finite number of labels in the program, which means we can't have an infinite subsequence of differing multisets. And for each multiset of labels, there's only a finite number of ways of arranging those into a query, which means we also can't have an infinite subsequence with equal multisets. And the actual proof is a little bit more involved than this, but this is the basic idea. Now, the proof relies on the number of labels being finite. But what do we do for non-type template arguments where there are potentially infinitely many different values? Like we might have an arbitrary precision integer type, which might have infinitely many different values it can store. The way we deal with that is, for integer types in particular, we invent a synthetic label that's all the integers. And for each integer, we assign it a count that is the absolute value of that integer. So for example, if our query is, we're saying if a pair of array of 5 ints and an integer between -8 and 7 is hashable, then we're going to form a count like this, where the synthetic number of integers is 5 plus 8 plus 7 is 20. And then we'll allow recursion if this sum of absolute values of integers is decreasing, even if nothing else is changing. And if the sum of the absolute values of integers is the same or getting bigger, then that's not going to be enough for us to keep going, even if the integers are moving around. For non-integer values, we have some ideas of what we might do, but for the time being, we're not handling those. So we basically just erase those from the query entirely before doing any of this checking, including the checking of if we've hit a cycle back to exactly the same query. And we have some ideas of what we could do better here, but so far we don't know whether it's necessary, so we've not invested in that. John?
Well, that's interesting. So you can actually you could do completely unrestricted computation and everything else, where you're making larger and larger types, but you could have sort of a Ethereum-like gas argument that you set to like 1,000, and as long as that eventually drops down by the time you get with the computation. So you can basically implement recursion limits.
Yes. Yes, exactly. We can implement a recursion limit in this by putting it in the query as an integer value. You could also do this without having integers, special case by having some kind of S of S of S of Z representation for your integers.
This is probably a weird case, but what if you wanted to do, I forget what the sequence is called, but it's like you take a number, it's odd, you multiply by 3, add 1.
Callout sequence.
Callout sequence. Would that work? Because obviously in some cases the number increases.
We would say when we see the number increase and you get back to the same impl, we would reject. As John was saying, you can make things like that work by adding a gas parameter, which is like just having a separate counter that's counting down. You'd need to make sure that's in a separate label than the integers, but there are ways of doing that.
If I understand correctly, that's done in very early stage of the compilation, which basically says a lot of, right? Because you don't need to actually have the model. Because we're parsing so that's probably really good for the compilation time.
Yeah, well, I mean, we hope that this whole mechanism is going to be very efficient to type check. That's one of our goals here, is we don't want to have a type checking procedure in Carbon that's extremely expensive, that's going to grow quadratically or worse with the size of your program. And so a lot of the design ideas here are how do we do this in a way that's better constrained than that? Yeah.
So this can, of course, still, like produce, like you can reduce in one thing and double the size of another thing.
Yes.
Do you also have implementation limits?
At the moment, we don't have. So the question was, this allows you to reduce in one dimension, but increase a lot in another dimension. Do we have any implementation limits on that? At the moment, we don't. I think there's still an open question there of whether we want something in that space. But for the moment, we don't.
Is the motivation to use the sum of all the integers instead of treating them individually just to reduce the label count?
Is the motivation of using the sum rather than treating them individually to reduce the label count? I mean, that's part of it, but really the big thing is when we're comparing two arbitrary queries, there can be integers appearing in different places in them. And so figuring out if it's the same integer or not is tricky. And taking the sum seemed like a fairly straightforward way of dealing with that problem. Okay. So what does this rule give us? We get precise errors from this. We don't get a giant stack trace. The first time you get back to the same impl with a query that's more complex, we can immediately say, hey, something's going wrong here. We think we're not making progress. And we can say why we think we're not making progress. So in this case, if we get from vector of i32 as hashable to vector of i32 star as hashable, we can say the number of stars is increasing here and nothing else is changing. Everything else is like, we've got the same number of everything else. And so we think we're not making progress, which gives us precise early diagnostics. This also always terminates without an arbitrary limit on the implementation, an arbitrary iteration or recursion depth. It's also composable. If two libraries are independently staying within the bounds we specify here and you use them together, the result should also stay within those bounds. And the behavior should be fairly predictable. Because we can produce an understandable reason why we think we're not making progress, we hope that users will be able to understand that as well. And as John pointed out earlier, thank you for that, we can still express any computation where the time bound is itself computable by adding a so-called gas parameter that you initialize in some way that you compute based on the query. But the downside of this is that this is no longer fully general. It's no longer Turing complete. You can no longer perform arbitrary computations while doing impulse selection. And we don't know whether this will disallow any really important use cases that we feel we need to accept.
Couple things. So you mentioned a guess parameter. Does that mean like you could theoretically feed in a guess parameter of like 1,000,000, and then every time you do a recursion, you just decrease by 1, and now you've effectively emulated recursion limits?
Yes, you can emulate a recursion limit by using a parameter like that that's a number that counts down with every step.
And additionally, I realize it's an open question of whether it's even useful, but have you considered doing something like just a, turn off this thing, I know what I'm doing feature?
Have we considered a turn this off, I know what I'm doing feature? I don't think we have. No, it's not something we've looked at. Maybe it's something we should have. I'm not sure.
Now, am I right in thinking that, with a little rewriting of your code, you could go, if you can pre-compute an integral loop variant for the recursion, then this will cover it? That any use case where you could do that, you could cover it? Because that seems pretty general.
Yes, I believe that is correct. Probably the easiest way of doing that would be to add a parameter to the interface. Okay. So in summary, having a type checking rule that is guaranteed to terminate is a hard problem. In Swift, the compilation may time out. There's no explicit limit that I could find. C++ and Rust seem to use a recursion limit. Carbon has a rule that is, at least in theory, always terminating. And the Carbon rule is also not really specific to Carbon at all here. We think this could be used in any of these other languages as well, if they chose to, and if it proves that it works well in practice. All right, and now I'd like to hand over to Josh, who's going to talk to you about coherence and specialization.
So, okay, now I'm going to, thank you, Richard. I'm now going to talk about the next hard problem, which is coherence. So what's coherence? So coherence is about, oh, let me do this. This will be a lot easier. Coherence is about, we want the meaning of code to be consistent. This idea manifests in the C++ world as the one definition rule, where we insist that names have the same definition no matter which translation unit is referencing that name. But if there's a mismatch, the program is ill-formed, no diagnostic required. For generics, we have this concept of trait coherence from Rust. And trait coherence is about interface implementation consistency. This means that if we have a query asking for an implementation of a trait and type, you always get the same answer no matter what file you're in. But not all checked generic systems are coherent, including Swift. So this is a language design choice again. So now I'm going to extend the terminology decoder ring from part 1, since we're going to talk about all these different languages again. So we have, in addition to protocols, traits, and interfaces, in what Swift calls a conformance, Rust and Carbon calls an implementation. What Swift calls a module, which is like our unit of dependency here, Rust calls a crate, and Carbon calls a library. Okay, so what can you do in Swift without any of these coherence restrictions? And let's do an example. So we have a MyGUI module that defines a protocol, and a different module, a formatting module, defines a type. And a third module, the widgets module, defines a conformance of that type for the protocol. This is called a retroactive conformance, since the conformance is provided by a separate module than the ones providing the trait and the protocol, the protocol and the type. And now an application can use this widgets module to get that conformance. We have this great result. We have glue code provided by a third module, that allows these two modules that are independent of each other, don't know about each other, to work together. So though, what happens when two modules both provide conformance for the same type and protocol? So generally, the Swift compiler will look for a conformance in the dependency of the current module and use that to instantiate any generics that it calls. So each module will use its own conformances, and that's probably work fine. So now, what if we had two modules that were interacting with the same hash table, and each module had a different implementation of hashable for like a single type? You could end up in a situation where you have subtle bugs, where entries added by one module using one hashable implementation are not visible in another module using a different hashable implementation. Now, these problems are rare in practice. It involves passing objects between unrelated modules. But if they do occur, if you do run into this problem, it's going to be pretty surprising and maybe a little bit hard to debug. So a similar disconnect can arise when using a dynamic type test to find a conformance, or when using a shared library that contains a conformance that is also defined in the application. So this is another regret, allowing a retroactive conformances. There's a regret by Swift designer Jordan Rose that he described in his retrospective. I bet this is all the blue here are links. You can, if you go to our slides, you can click on that and see how he described his problems. And it was just going to be discouraged going forward in Swift. They're adding a warning to Swift to say, don't do that. You can disable it on individual cases, but the guidance is going forward, moving away from this.
Question. Is the guidance to not do retroactive conformance?
Yes.
Okay.
The guidance is, please don't make retroactive conformance. You can opt in to allowing them if you need them for some reason, but prefer not to because they cause problems. So now Rust. Rust, we do have trait coherence, and it uses a combination of orphan rules and overlap rules to achieve coherence. Now, the terms orphan rules and overlap rules are not necessarily specific to Rust. Other languages do have orphan and overlap rules, but the rules themselves are different in different languages. So talk first about the orphan rules. Orphan rules restrict where an implementation may be defined. And this is to ensure that, and this is like avoiding the retroactive conformance problem, because you want to be absolutely sure that if you can use an implementation, that the implementation will be found in a dependency you're guaranteed to be importing. So there's a restriction on where implementations can be defined. If you define an implementation anywhere else, it's called an orphan, and that's an error. So adding to our terminology decoder ring one more time, retroactive conformance in Swift corresponds to an orphan in Rust or in Carbon, which I'll get to later. So Rust also has an overlap rule, and that overlap rule says that no two implementations may apply at the same time. You have the same type and same trait. You can only have a single implementation that applies. And this is as restrictive a rule as you can have. And overlap rules in other languages can be less restrictive. Like, for example, Carbon has a less restrictive rule. We'll talk about that later. And this has a big consequence, right? It means that some implementations are not allowed at all. And that's because if you had that implementation, then there could be another library that could define a conflicting implementation. And we want to allow composition. So they have rules that say, well, we allow you to only have this implementation, not that other implementation, and in order to avoid the possibility of conflicts with independent libraries. So I'm going to illustrate with an example. Imagine we have two crates, one defining a trait, the hash table crate, and another defining a type, the company crate. Now, if you have the type, the crate with a type, depend on the crate with a trait, then you can define an implementation with the type. So the rule is that if you have an implementation with a local type, that's allowed, where local means defined in the same crate. If the dependency is in the other direction, then you can have an implementation with a local trait. But if we have three crates, an independent crate, you can't have an implementation in that separate crate. That is not allowed. So the rule is, if you have a local trait or a local type, it's not an orphan. And this is enough to get our property that we want. If only crates that could use that implementation must already depend on both the trait and the type. So this gets us our coherence property. But notice how the dependency relationship between the crate with a trait and the crate with a type determines where, or even if, the implementation can be defined. Like if there's no relationship between those, no dependency relationship, there may not be any trait, any crate that can define that implementation.
Cool question.
Yeah.
Do default implementations affect that at all?
There's a lot of complexities here.
I imagine they wouldn't.
Default implementations are not currently supported by Rust. Those are that requires specialization, which is, that's my understanding.
I thought they did. I might be wrong.
I think that is an unstable Rust. And in addition to default implementations, there are a lot of other complexities that we can get into here once we allow parameterization, so that you can have parameterized types, parameterized traits, parameterized implementations. And so now we have this problem that you can, like, if you have, say, a parameterized implementation, maybe you have a very broad implementation, a very specific implementation. Those two implementations or more could apply to the same query. And that would be a violation of our overlap rule. So we need some restrictions that say to prevent these overlaps. And to quote one of the Rust coherence protocols I have up there, every impl that is legal to add in a child crate is also an impl that a parent crate cannot add. There's this tension there because to avoid conflicts. So for example, let's say we had an implementation of a trait for any type satisfying a criteria, which is called a blanket implementation. So maybe this implementation serializes the type into a string and then computes a hash from that. So the orphan rules we had require this implementation to be local to the trait, which allows the compiler to do a local check that there aren't any overlapping implementations, maybe two blanket implementations that could overlap. But even if that blanket implementation is legal, because it's in the crate with the trait, it could still conflict with an implementation in a child crate, maybe a more specific implementation. Of course, no child crate could add that conflicting implementation if the blanket implementation exists from the start without giving overlap error. But that means that adding the blanket implementation later is actually an incompatible change. So this is a restriction on not just on where you can define things, but on evolution. The root cause of these problems is that Rust has no way to resolve conflicts between implementations. And if there was like a specialization rule, then maybe we can solve some of these conflicts. But there's no specialization rule that's made into stable Rust, as that point's been made. If we did have a specialization rule, we would avoid reporting error and would allow to resolve these conflicts. And these kinds of rules can be coherent as long as any implementation query gets a consistent answer across the program. So RFC 2451, you can tell from the name here, rebalancing coherence, that there's been a number of changes in how the rules, as with time, how these rules have changed. And these rules have become a little bit more complex with time in order to have more carefully draw this boundary so that you can carve out these important use cases that they wanted to allow where an implementation can be written without risking overlap with other libraries. I just want to point out that these rules end up making the order of parameters potentially significant. So now let's compare with Carbon. For Carbon, we're leaning into specialization in our coherent story so that we can pick between overlapping implementations. This both simplifies the rules and imposes fewer restrictions. And we can do it consistently as long as we can ensure that when we're applying the specialization rule, it's always seeing the same set of implementations. So we need them to be visible anytime we're looking potentially could be doing a query for them. And much like Rust, we get this by enforcing an orphan rule. And also like Rust, that's involve a requirement that some part of the impl declaration be local. So I'm going to illustrate the orphan rule in Carbon with some examples. So just like in Rust, a local type means it's allowed. Similarly, a local interface is allowed, but also a local type parameter would be allowed, or a local interface parameter. That's all good. But in this example, all of these types interfaces are built into Carbon. So there's nothing that would be forcing a library that contains this implementation to be imported in cases where it would apply. So nothing is local, it's an orphan, and that's an orphan error. In this example, there's constraints on the type parameters. This one has a local interface, and this one has a local type. Again, there's nothing forcing this library to be imported in cases where this implementation applies, so it's again an orphan error. So I can now state the orphan rule in Carbon succinctly. An implementation is allowed as long as anything in the type or interface part of the declaration is local. And just like in Rust, the orphan rule restricts any given implementation to at most a single library, just like before. And it follows from circular dependencies being forbidden. That means that the dependencies themselves will force only one library that's allowed to declare this has access to all the names that you need to declare it. So again, this is a trade-off in language design. Coherence reduces surprise, but it gives users less flexibility about where they can define their implementations. And for Carbon, this coherence aligns well with our priorities. We want to have very predictable behavior, low context sensitivity, and to support local reasoning. So, but then we have this problem, right? What happens when we have two independent libraries that we want to combine? And like we could with the Swift system. So here I'm doing an example. We have 3 packages, and one of them defines an interface and a function, a generic function that requires the types that you pass to it implement that interface. We have another package, unrelated, no dependency relationship, with a type. And then we have our program, which wants to use both of these together, but it can't pass the type to the generic function because it doesn't implement the interface. So if we try to implement the interface, we're going to get an orphan error. So what we do is we use an adapter type. So this is a Carbon thing where adapter has the same data representation as the type it adapts. So you can cast between them, including pointers of those types and freely. So from part 1, you may remember I talked about the extend keyword. This means that the adapter has the same API and inherits the API of the original type, much like you would a base class. So now we have a local type, and so we can implement the interface for this local type without running afoul of the orphan rules. So there are other ways of addressing this problem, and it's good that we have choices here that helps offset the costs of using coherence. And what I just talked about is really the Carbon contribution in this space. So, summary. C++ require consistent definitions, but may not diagnose violations. Swift has not enforced coherence, which has led to problems and is now adding a warning. Rust does enforce coherence, but it has a no overlap rule that imposes complex restrictions on which implementations may be defined. Carbon also enforces concurrence, but it has a simpler rule that allows more implementations. And the power of this really hinges on resolving overlaps using a specialization rule.
Just so if I understand correctly, you need to explicitly introduce every type from your library. Sorry, explicitly introduce every type from your library, naming it using this keyword. But is it right?
So
is there maybe if that's true, is there a way to do it like do something like import and then have all those things defined with your original names in your users scope?
So yeah, in Carbon, when you do an import, the import always imports within the package name. There's nothing that automatically moves names into your local package.
Right.
And if you want to do that, you have to do an explicit alias. We don't have any feature to kind of automatically alias names,
So
but
maybe
we can do it by yourself.
So maybe the choice of name was wrong, but like maybe a different one. But so there's no feature. But how could you do it? Like you just need to do it manually.
You do it manually, just like you would write a using declaration in a header file. You could write an alias declaration in your package to kind of rename things.
Right. Maybe it would be useful to write something like that. I don't know.
okay. Other questions? Because actually, this talk of the specialization rule brings us to our next hard problem, which is that specialization is hard.
I just wanted to add one comment. I really like the adapt thing. That's a real pain point in Rust. If you're trying to get two libraries to talk to each other, you have a trait here, you have a thing here. It leads you to the new type idiom, except that's also hard.
Right.
You can do everything by scratch. Yeah.
Right. This is sort of like the new type idiom in Rust, but it's intended to be a bit more convenient because you don't have to forward all the methods from one to the other. It's just a convenience for making that idiom work much more smoothly.
Actually, slight side question. So suppose I'm using that third-party type in my package or my library. Do I have to convert everything in my library to using my new type in order to use that import?
So values only have one type. And the types determine the implementation. So unless you're using this new type, you're not getting the new
Okay, so
implementation.
you still have to use the new type.
You have to use the new type.
Okay.
But the conversion, we are guaranteeing that the representations are the same. So that conversion is free in some
So
sense. It's a no-op conversion.
Yeah, it's as if, so you should be able to seamlessly interrupt with anything that using the native type.
Right.
Okay.
Exactly.
So maybe really adding.
Other question? Okay. Specialization. So what is specialization? This is when you have multiple implementations for the same that are applicable to the same type and interface combination, and we're going to pick the most specific one. So if you imagine you have a sort interface, maybe there's an implementation that's very general that works all the time, that even link lists, but there's a more specific implementation that works when you have access to random access to the container. So in C++, we really like the performance benefit that you get from supporting specialization. Rust has a long-term effort to add specialization, but that hasn't made it to stable Rust. Swift, as far as I'm aware, I don't know if it has any plans to support specialization of conformance. It does have type-based function overloading, which has some similarities. So diving into C++, the performance of benefits of specialization and support in C++ are great, but we have this problem that library authors have to be careful to avoid ambiguity errors when the compiler has to pick a most specific implementation. This is because there's only a partial order of specializations, not a total order. Specialization has been seen as the solution to Rust's overly restrictive overlap rules, and has been under consideration for the last 8 years. There were originally some soundness problems related to lifetimes that blocked this for a while, but those, as I understand it now, have been solved. But there's still problems that make it hard to add specialization. So, for example, given a blanket implementation, can the compiler use the value of its associated types? And without specialization, the answer is yes. So this code compiles, even with the return of 3. With specialization, though, a more specific implementation might apply with a different associated type. So this code would not be allowed. So this means specialization has to be added opt-in if you're adding it later. And it's much easier to include specialization from sort of the start when you're first adding the generic system. The other difficulty is that there are really a lot of ways of defining a specialization rule. You could use a subset relationship between the matching types or matching queries. You could use the dependency relationship between libraries to decide which is more specific. You could have restrictions on how implementations can relate to each other, forming a tree or a lattice, and lots more. There are lots more things you've been considered, and you have to really pick this in order to be able to, and there's trade-offs. So in Carbon, we looked at what we wanted to prioritize as part of a specialization rule. And there's 2 properties that were really important to us. One is coherence, which I've talked about at length. And composition is this ability to combine independent libraries without the possibility that the combination will trigger an ambiguity when trying to select implementation. This is good not just for combining libraries, but also allowing libraries to evolve. So our solution is to have a total ordering. And we use a tie-breaking rule to resolve those ambiguous cases, which means that there's always a most specific implementation and never ambiguity. The Carbon's rule orders implementations using their type structure. Or type structure is this thing I'm going to describe, where you take the impl declaration and erase all the type parameters. I'll show you via some examples. So we drop all the, in addition to the type parameters, we just drop all the constrained information about those type parameters and replace the type parameters with some placeholder. In this other example, you'll notice that the names left in the type structure are just the names that we use in the Orphan Rule to enforce coherence, and that's going to be important later. So all type parameters are replaced with the same placeholder, which means that this loses the information of whether the parameters are actually the same. And Carbon's specialization rule doesn't use that information to decide if a declaration is more specific. Now, to order the type structures, now that we know how to compute the type structure for every implementation, we want to pick one that's the most specific. And we do that by looking at the first difference, reading left to right. And we're going to pick the one that has a specific type in that position instead of a placeholder. So in this case, the first difference is at the beginning, and we're going to ignore all the other differences. And so we're going to prefer the first implementation. The differences might be in the parameter to the type. And in this case, you can see that the first declaration might be a proper subset of the other. And this rule has this nice property that the one matching cure queries will always be considered more specific when there's a strict subset relationship between the 2 impl declarations. The first declaration could be in the type parameters for the interface. And here, in this first case, you see that there's no type parameters, and that's always going to be considered the most specific. So now I've told you this rule. how type structures work and how we use that to decide which implementation to select. And I think this goes to the sort of question from part 1 that we heard. So in this case, we have 2 types, big int and fancy int. These are in different libraries, different packages, but they both implement an interface called int-like. And they both support addition with anything that implements int-like. And that's true, and they have implementations in both directions, so it can support in either order. So now what happens if we try and add a big int to a fancy int? So if the big int is first, its implementation gets higher priority according to the type structure rule. If the fancy int is first, the fancy int's implementation is higher priority. And the problem here is we really don't have any reason to favor big int or fancy int over the other, except the order in which they appear in the parameter list. And this is sort of the fact that we're getting a different implementation from a library, an implementation from different libraries, the price we have to pay in order to get a total ordering. We will see how this works out in practice. Carbon's an experimental language. This is one of our experiments. We think the choice of using nominal interfaces here is going to help us avoid a semantic breakage here, because we expect any given interface to have a single semantic meaning associated with it. Because this is not like ad hoc specialization that we have in, for example, C++, where the API can change for a specific argument value. So another thing came up in part 1 was when you have implementations with the same type structure, we're going to ask users to manually prioritize them. And this is a degree of control that users often want anyway. They want you could have complex rules about trying to say, well, if you have this sort of matching parameters or something that's more specific, easier just to let the user say what they want mean. And this is, if you have a lot of overlapping implementation, just giving the user a prioritization order scales better, because otherwise you'd have a combinatorial explosion of different possible intersections if you ask them to define what to do in each of those overlaps. So a consequence of the the orphan rule that I told you about earlier is that having and then using the same exact inputs is that having the same type structure means they have to be in the same library, which means that we can it makes it much more convenient to manually order them when you know that they have to be in the same library anyway. So this is a case where not only specialization simplifies coherence, but coherence simplifies specialization as well. These two work really well. These two really work really well together. So in summary, having a total ordering means no ambiguity when picking an implementation specialization, which means we can compose libraries safely and evolve libraries safely. Okay, so covered the 4 problems. I'm going to have one little bonus section where I'm just going to look back and see what the impact of generics is on the non-generic parts of the language. Because we really want certain things in the non-generic parts of the language to support generics. And this has led to very different foundations for the language in Carbon than C++. So for check generics, we want name lookup to not be very specific. Not very context sensitive. This is good for readability. Readers of the code don't want to have to figure out where they have to look to find out what something means. But it becomes not just nice to have, but actually really necessary if you want to have code to have the same meaning, whether it's generic or not. And also for type checking, right? You want to be able to say what the signature of a function is. And you can't do that if you can't resolve the name lookup without knowing more information that would be available when you're calling the generic, or inside the body of a generic. So Carbon has package name spacing, which we talked about just a bit. No argument dependent lookup. No open overloading, which is where like the set of overloads might vary depending on which file you're in. And all these to reduce consecutivity. And you'll notice I'm talking about these as like features, but really we're talking about, in some cases, removing features. And removing features is also helpful. Like ad hoc specialization makes it basically impossible to do type checking of generics, because how can you type check vector T if you don't know T? Because the API could be different if T is bool, right? That's just a problem we can't get past. Circular dependency showed up in a way that at least surprised me. The whole deal with the coherence and specialization felt more like a discovery than an invention to me. The coherence that we talked about with trait coherence is something we see as being valuable across the whole language. We want those sorts of consistency. We don't want the meaning of code to change as you add a new import or whatever. And this is very important in our belief for scaling up your code, like having lots of developers working on very large code bases. We really want that consistency so that you don't need to get that local context to understand what's meaning. And coherence and specialization, individually good, even better together. So last thing I want to talk about that really benefits check generics is anything you can do to simplify the language, particularly the type system. But in Carbon, interface implementation is the only method for open extension, and it's the only method for specialization. And that means there's only one way to overload an operator. There's only one way to iterate through a container, and so on, all this stuff. And simplicity is just, when it is super important here, and really, really affects the complexity of the generic system. Okay, conclusion. Talked about 4 problems. All these problems are hard, but we think we now have good solutions to them. These solutions support efficient compilation, clear error messages, and programming in large. And by programming in large, I mean large teams working on large projects over long time periods. And plus a little bonus thing about how this impacts the rest of your language. Are these the only problems you think implementing check generics? Any guesses? Well, check generics is an active area of research. A lot more problems than ones I've talked about here. This is just a sampling of some example problems that people run into, are working on. These are problems that Carbon is working on some of these, Russ is working on some of these, Swift is working on some of these. For example, this first problem, check periodic generics. Swift has active proposals. I don't know the status of these. Some of these may have actually even landed, having checked periodic generics. And Carbon has a proposal introduced in the last week. It's still open for discussion. You can go comment on it right now if you're interested in variadics. And we in the Carbon team promise to keep working on this. We are continuing to work to find good solutions here. And the issues that arise with implementing check generics and contribute these back to the community. We're working in the public and super happy to share our results. Questions? Yeah?
So right now in Carbon, do you have a function where one type is constrained by a check generic and the other one is a template type?
Right.
You can do that. Oh, wow.
Yes, you can have in Carbon, each parameter is marked as either well, it can be check generic or template, and they can be mixed. And this is, we consider important so that you can incrementally migrate from templates to check generics. So you can do that one parameter at a time.
So are there plans to eventually remove templates from Carbon?
The question is, do we eventually plan to remove templates from Carbon? I think our goal is to make the check generic system as good as we can, to leave that door open, but we don't actually see that as necessarily being viable because there may be some things that have a more like maybe metaprogramming feel, that where templates are actually more of a natural fit. Like maybe if you wanted to reflect on a type, maybe that needs to be a template parameter rather than a check generic. Yeah.
And C++ interop.
And C++ interop, which we expect to be a problem for long term. Yeah.
I'd like to understand better. Suppose I'm writing like a geometry library, and there's like a set of primitives like rectangles and so on, and it can extend. And there's a set of algorithms like intersection and so on. So in order to like implement each algorithm for each primitive or pair of primitives, how do I organize this code?
So the question is, we have geometry library. It has a bunch of types that correspond to shapes and a bunch of algorithms that want to work on all these different kinds of shapes. How would we organize the code? So we could use generics. Rust doesn't have inheritance, which would be another way to approach this problem. And where you could represent that in Rust or in Carbon would be to use either trait or an interface to represent whatever API the algorithms need to ask of the shape, and have all of those shapes implement that interface. You could also have a common base class in Carbon, because Carbon will support inheritance as well.
Yeah, but each algorithm for each shape is different.
You're saying, so are you talking about maybe a double dispatch problem or something like that, where you want to specialize, you want to have
specializing for like two orthogonal things?
So, I mean, I guess it would depend very much on the specifics, but you definitely, the intent here is the problem we're trying to solve here is when you have different implementations for different types of a common interface. So if you don't have a common interface, this may not be the right solution.
Sounds more like overloading to me.
You could do this with overloading. Carbon, we don't want open overloading where you can do arbitrary additions to a given name from mixing from different libraries. But we do intend, at least because of C++, to support closed overloading, where you have one function and a fixed set of types that it can be applied to, which might be more appropriate for that particular problem. Other questions? I do have some more resources, including links to the proposals that have that specifically talk about the solutions to the hard problems I discussed in part 2. Richard and I discussed in part 2. Also how to get started on Carbon, links to this talk, and so forth.